Work and kinetic energy. First, I want to talk with you about work with a constant force. Work and energy values are scalar, which means we're not interested in direction when we're talking about work and energy. And it also means we aren't concerned with vector math when we're adding work values or adding energy values. Now, work is defined as the applied force to an object that is parallel to the displacement of that object. The force will be in the unit of newtons. The displacement is in the unit of meters. So the unit for work can be a newton meter. Also, it can be called a joule. Our first example is we have some sort of a block on the ground. There is an applied force at some angle to the horizontal. We're going to assign direction. We'll make right positive plus x, up plus y. And we're going to give some values here, some givens. The applied force is 1 Newton. The angle is 30 degrees, and this object is going to be moved a displacement to the right of 1 meter. So that displacement to the right here, some displacement to the right. All right, let's start with drawing a free body diagram. The first force that is already given is this applied force. We also have a weight acting down from the object, and we have a normal force acting upward. And also we have components of our applied force, so I want to go ahead and draw the components of the applied force, and we're going to draw those on the side. So if this is the applied force, F applied, then we can draw the components of it. This would be F applied x, and we have an F applied y at some angle. So far we've drawn a picture, we've written the given. What I want you to find is the work done on this crate. So the formula for work is the force applied to the object multiplied by the parallel displacement. And so if the displacement is to the right or in the x direction, I want to add up all the forces in the x direction. In this problem, there is just one force in the x direction, and that's the F applied in the x direction. We're going to multiply that by the displacement, and that will give me the work done. So by plugging in the numbers here, my F applied x using trigonometry is going to be F applied cosine theta multiplied by my displacement. Now we can just plug in numbers. My F applied was 1 Newton, cosine of 30 degrees multiplied by, say, 30.0. Let's make that 3 sig figs. Bring that up here. Multiplied by a displacement of 1.00 meters. Okay, so that answer comes out to be 0.866 Newton meters. And that, folks, is also known as our SI unit for energy, which is the joule. Notice my answer is in 3 significant figures. And, okay, we'll go on from there. Alrighty, our next example, we have some block. It's moving to the right. There is friction involved, and there are no other forces applied in the horizontal direction. Because there's friction, this object will eventually come to rest. In this drawing, it comes to rest in 1 meter. The mass of the object is 1 kilogram. The acceleration due to gravity is 9.8 meters per second squared. And the coefficient of friction between the object and the ground is 0.2. 0.70. The question I have for you is, what is the work done on this block? And it's always due to the force that's being applied to it. So in this case, what is the work done on this block due to friction? So first thing we're going to do is draw a free body diagram. There are three forces acting on this object. One is the weight, the other is the normal force, and lastly is the kinetic frictional force. Remember, friction acts opposite to motion, so my kinetic frictional force is going to be to the left. Now, my formula for work is going to be the force multiplied by the parallel displacement. So the force in this case is the frictional force, as we've already talked about, but we also need to assign direction. So let's do that. Let's make right positive plus x. And when we do that, we see that my frictional force is left. So when I plug that in, we have a negative F sub k multiplied by my displacement. And then what we need to see here is for frictional force, I need to use the formula that we know for frictional force, which is the normal force times the coefficient of friction multiplied by our displacement. And the normal force, recall, if you are on a level plane, then your normal force and your weight can be the same. So in this case they are. So plugging in weight for normal force, we get this expression. Now we're ready to plug in numbers. This is everything we have. So the mass is 1 kilogram, G is 9.8, the coefficient of friction 0.70, and the displacement was 1.0 meter. So my answer is going to be negative 6.9 Newton meters, or my work is going to be a negative 6.9 joules. Notice I rounded my answer to two significant figures. Okay, time for example number 3. Alrighty, example 3, we have some person holding onto a red ball, and they are walking to the right, so the ball has a displacement to the right. But the force being applied to the ball while the person is holding it is a force upward. We'll call that F applied, F-A-P-P. And the only other force acting on this ball is the weight of this ball, I'm calling mg. So the force applied to this ball is actually perpendicular to the displacement of this ball. And since work is equal to the applied force multiplied by the parallel displacement, and there is no parallel displacement, the work in this example is 0 joules. Interesting. All right, let's look at example number 4. Now, what if we have more than one force acting on an object? We're going to say the net work acting on an object is equal to the net forces acting on an object that are parallel to that object's displacement. So we have an object. It is moving to the right. It is going to move a displacement of 1 meter to the right. There is an applied force at an angle of 29 degrees above the horizontal of 9.9 newtons. There is a coefficient of kinetic friction between the block and the floor of 0.70. The block has a mass of 1 kilograms. And your object is to find the net work on this block or this crate. And the first thing we're going to do is we're going to draw a free body diagram. So we're going to draw the center here. Our first force is that applied force. We have the weight of the block. We have the upward normal force. But we also have a frictional force, a kinetic frictional force, which is opposite to motion. So here is our free body diagram. On the side, I want to go ahead and draw the components of my F applied. We will be needing those components later. So my F applied is going to have a component this way, and it's going to have a component that way, this angle here. We'll call this F applied cosine theta, and the vertical one we will call F applied sine theta. Again, our objective is to find the net work done on this crate when it moves one displacement of 1 meter to the right. Also, let's go ahead and assign direction. Let's make going to the right plus x, and we can make up plus y. Okay, we're ready to talk about formula. Now the formula is the net work applied to an object is equal to the net force that is parallel to the displacement. The displacement in this problem is horizontal. So what I want is all the forces that are horizontal. I'm going to add all of those up. And there are 2 forces that are horizontal. So let's do a side note. Let's just find the net forces that are horizontal. I'll call them x in the x direction. I have a negative frictional force, and I have one other, which is the F applied cosine theta. And I want to find the value of these 2 and put it in my original equation for net work. If you look at this a little bit closely, I do not have a kinetic frictional force, so I will need to use the formula for frictional force. And the formula for frictional force is, the formula again is the normal force times the coefficient of kinetic friction. So when you look at our given, we do have an applied force, we have an angle, we also have a coefficient of kinetic friction. We do not, however, have a normal force. So what we're going to have to do is also sum up the forces in the y direction to find out what is that normal force. So just going back to the original diagram, let's see if we can figure out what the forces are in the y direction. So in the y direction, we have a normal force, we have a weight, and we have a vertical component of the applied force, which is the applied force sine theta. And we're going to combine all 3 of those to ultimately find the normal force. So let's go ahead and do that. I'm going to scroll up, see if we can. Then we're going to sum up the forces in the y direction now. And that's going to be a positive normal force minus the weight of the object plus the applied force in the vertical or y condition, which is the applied force sine theta. So, and in the y direction, there is no acceleration, so that is all equal to 0. So my normal force is going to be the weight minus the vertical applied component. And by plugging in the numbers there, let's get a value for normal force. We're going to get 1 kilogram for the mass, 9.8 meters per second for the acceleration due to gravity. The applied force was 9.9, sine of 29 degrees. That normal force value, then doing the math, should come out to be 4.85 newtons. This normal force value now I can use to put in my above equation for normal force in my sum of my forces in the x direction. All right, so let's plug in some numbers now that we found normal force. So for the normal force, we'll plug in 4.85 newtons. The coefficient of kinetic friction will be that 0.70. I have an applied force of 9.9 newtons times cosine of 29 degrees. This should come out to be 5.3 newtons, sum of the forces in the x direction. Now we just need to find the net work, which is the parallel force. In this case, it's the sum of the forces in the x direction multiplied by the displacement. So 5.3 newtons multiplied by 1.0 meter gives me 5.3 joules. All right. Okay, we have a hiker with a red backpack. And the question is, what is the work done by the hiker to move the backpack at displacement in green I have here going up the incline? Now we already know work is going to be the force applied, in this case it's the force of the hiker, multiplied by the parallel displacement. So I want to go ahead and draw the forces on this backpack as the hiker moves up this incline. And so this backpack has two forces. One is the force of the hiker upward, but there's also the weight of the backpack itself. And that's the same thing up here. We have the force of the hiker and then the weight of the backpack here. We're interested in the force of the hiker. And you also notice I'm interested in the parallel displacement. So although the person is walking along this incline, I'm really only interested in this height distance here because it is this distance that is parallel to the force of the hiker. So this ends up being the force of the hiker multiplied by the height because it's parallel to the force of the hiker. Now what is the force of the hiker? Well, if the backpack is not accelerating upward or downward, so to speak, in the beginning of this picture, we can find by using Newton's second law of motion, sum of the forces in the y direction, we could say the force of the hiker minus the weight of the hiker is equal to ma(y), which is also 0 because it's not accelerating upward or downward. So therefore we can say that the force of the hiker is equal to the weight of the backpack. So we can set that equal to mgh. We want to find the work done by the hiker on the backpack. So just finishing this problem out, plugging in the numbers. Here we go. The work done by the hiker is the 15 kilograms multiplied by the 9.8 multiplied by the 10.0 meters. And that comes out to be 1,470 joules. Okay, here's your practice problems. These will be due our next class meeting, and then we can go over the practice problems, and we'll also go over your quarter tests that you took Thursday and Friday. Have a great weekend.